This is the third and final video in the series on testing and troubleshooting the PixiFlood LED driver. As covered in the previous videos, I conduct a series of tests at the end of each stage of assembly. In Part 1, we covered the test for passive and power rail components. In Part 2, we covered the test for the components that control on, off, and dimming. Please watch the first two videos prior to this one. You should be able to find a link to them in the description below. This video will start with the test that should be completed before you attach the LED, followed by what should be tested at the completion of Stage 4. By definition, at the end of Stage 4, you have a fully assembled driver that is ready to be installed into a floodlight housing. The initial focus of the outline test will be on the delivery of signals to the LED. I strongly recommend this testing is completed before you attach the LED. You really don't want to deal with the LED light and the associated heat. Finally, I will attempt to go over considerations of testing on a fully assembled driver. What has changed and how to deal with getting the required test readings to figure out what's going on. Since this is my third video, I hope it's better than the previous two. Let me know what you think. You now have a decision to make. Do I go through the full series of tests? Or do I just check the LED supply signals and then assume that if the supply signals are correct, that everything else is fine? I typically go through the complete series of tests. The reasoning behind that is I don't want to have to open up an installed floodlight to deal with an issue at some point in the future, and I believe the full suite of tests really don't take that long to do. The complete series of tests consists of starting with the passive tests, which were covered in the first video, followed by the power rail test covered in both the previous videos, followed by the color control and dimming test covered in the second video. If they are all fine, we can expect the proper signals are being sent to the LED. I'm not going to show you those tests now. You can review the previous videos to find them. I'm now going to focus on the LED test points, which are shown here. What color goes where is totally dependent upon your specific LED. I have seen both RGB and BGR LEDs being purchased. Truth told, it doesn't really matter for what we're going to be doing, but for my test descriptions, red is the outermost set of contacts, followed by green, then blue. As stated in the previous video, you must use the negative test pad and not some form of common ground from within the circuits. You can, however, use a common vent connection if you want to test all three. Let's set expectations on the readings you should get from these test points if everything is functioning as expected. Since there is no LED to consume some current, your reading should match the voltage inputs from what I've referred to as the 12-volt test pad. The focus of the test are on these 6 points. You use them in 2 in a pair. With my power turned on and color none, you can simply walk through and check these 3 test points, and they should yield a near zero reading. The reason why you can use a common test point, and to be honest with you, you could actually use it from here and then use these 3, is in the design of the circuit and the way the board is laid out, is this VIN is for input into the PT4115. It's not driving it out over here. What is driving it out to these test pads is actually coming off of a combination of the 12-volt bus, and then the current sense resistor is monitoring that bus to see how much current is being consumed at the corresponding test point. So for our test, we really don't care about that. It's just a 12-volt line to here. So what you're able to effectively do then is to use a single test point on the positive side and then conduct all of your measurements using one of the 3 negative test pads. And the reason for that is the negative side is being driven off a switch. Through the inductor, and then it comes back up here. So with that understanding of the circuit design, it makes it easy to test. So what you simply do is step through red, got the appropriate reading, check your green and blue, they should have no voltage. Step to green, no voltage. I've got my 12 volts here, no voltage. Step to blue. Again, you step through the 3 test points. That's all there really is to it. If all 3 test points read out appropriate, attach the LED. You're ready to go. Now, let's talk a little bit about that decision. Well, why didn't I just go ahead and attach the LED and see if it turns red, green, and blue? The answer to that question is, what if, yes, there's current that'll turn it on, but let's say it's high versus low current. So instead of a hard, solid red, I'm getting a half red. At that point, you're going to have to deal with the LED, which says you can't run it for long periods of time, and it's going to be shining in your eyes since you're going to be looking at these test points, and you're going to have to be probing on this side. So you're going to have to deal with that light. And what I've just learned over time is, I've now assembled quite a few of these, is it's not worth dealing with the spots. And I can tell you that you look at that LED, you're going to see spots. So by doing this set of tests without the LED, I know that I'm getting the full 12 volts over here. Therefore, I also know that it's going to be a good solid light. And so for measuring from LED driver to LED driver, I will have some consistency. So the colors will match and everything else. But I can also tell you there have been many times where I've reached a point and says, you know what, I'm in a hurry. I'm just going to put it in and deal with it. If I can't, then I end up finding myself covering it with my hand. And that's just the problem of then trying to get around and get everything else. That's why it's decision. You can make a decision to do it the easy way, which is hook up the LED, and if it turns red, green, or blue at the appropriate time, you're done. Or you go through and do all the tests before you hook up the LED. I'd like to move to considerations of a fully assembled board. These considerations can be broken down into 3 groups. First one is, wow, I now have an LED. The second one I like to refer to is dealing in a crowded space. And lastly, okay, I got all this stuff hooked together, how do I figure out what's broke? Up to this point, we have been dealing with a driver board that did not have an LED installed in it. Once you've installed the LED, there are some things you need to be aware of as you go through and test or troubleshoot. I've already touched on 2. One is, now that this is working on some colors, it will generate heat. Heat will damage the LED or shorten its lifespan. So you want to make sure you do not run it for a large period of time, so heat can build up and shorten the lifespan or actually even destroy the LED in your test. The second option, or second thing to consider, is having to deal with the source of light here, this light source. It is bright and will cause you to see spots and potentially damage your eyesight. Those are 2, and I think they're very significant, but there are others as well that you have to deal with. Without the LED, there is no current to be consumed. The voltage will flow on both of these, and we've been able to read the voltage, but current is what is actually being consumed by an LED. And that current is then turned in to generate light. Since there's no LED, there's no current being consumed. The PT4115 is a constant current driver. Its role is to make any adjustment required to maintain a steady flow of current to this device. As you may be aware, current is a function of the delivery of electrons on the negative side of the circuit. Voltage determines the volume of electrons that are being pushed. The PT4115 will make adjustments based upon its readings from the CSN switch off of these resistors and the 12-volt rail, saying, okay, I see it's consuming this much, and we'll adjust the voltages to ensure that the proper amount of electrons are flowing. So that's why on the negative side you can't use a common ground, because it's actually making the adjustments on this side for voltage to ensure the right volume of electrons are flowing. Up to this point, we've been able to take test readings here and get a very consistent reading that is at or near the VIN. With an LED in place, that is no longer true. The voltage is going to be a function of the consumption of current. If you read the data sheet for a LED, it will provide forward voltage, i.e., how much voltage does it expect to deliver the right amount of current. In the case of a red channel, the LEDs that I use take between 6 and 8 volts. The green channels take between 9 and 12 volts. The blue are between 9 and 12 volts as well. However, if you'll notice, that is a range. Each LED can be different, and it's within that range that you will take a measurement and say, okay, I'm within that range. But if I'm testing red and I get a reading of 6 volts, is that good or bad? Well, it'll depend upon if you're getting the color intensity that you A, expected, and 2, that you requested. If you request a dark red, it will require less voltage. It will require less current because it's not lighting this up as much. So you will see voltage differences based upon the color that you requested. So in testing it, you want to make sure that whatever you're using to test is using a very consistent color. It's always sending the exact same RGB codes when you take your measurements. That's a big difference. The other part that I would also like to make sure you understand is LEDs come in different orders. This one is red, green, and blue. But there are blue, green, and red. These 3 points map to these 3 points. So if you're working with a driver and you have a blue, green, red LED, and you see blue, you see green, you need to make sure you know which line is being lit up or which one's not being lit up, so you can know which is the appropriate set to go against. You just can't assume RGB, because over here may be R, and remember, the board is colorblind. All it sees is I'm sending current, and that current needs 6 volts, or that current needs 7 volts, and so it will make that adjustment. That's also why there are 3 different sets of electronics, and that is to cover and be able to make adjustments on each individual color, but they're not tied to any color. It literally comes down to what's hooked here will drive what's hooked back here. Let's move to the next set of considerations, what I like to call dealing with crowded issues. When you look at the board, you will see it's very tight. It's dense. Once we get all the inductors in, it becomes very difficult to get readings out of the test points. Blue one, you want to know what's going on? It's over here by itself. Not a problem. But if you want the green one or the red or blues, red or greens, as you can see, they're in tight. Depending upon how your transistors or your inductors how well they're standing up or whatever, you may not even be able to get to them. So one of the things you need to learn is on a crowded, dealing with the crowd, is how to get alternate test readings. The inputs out of the WS25 are a piece of cake because of the resistors. When you look at the resistors on the back side of this strip, there's a 1-for-1 match. For example, this bottom one is the WS2811 blue output. This one would be the WS2811 green output, and this one would be the WS2811's red output. So if you want to know what's coming out, you can check it here. You don't necessarily have to fight to get in. So the mapping is, this one is the same reading as that one. This one is the same reading as this one. And this one is the same one that's kind of hiding under here under the capacitor. So that's one set of simple tests that you can substitute for. However, if you go back and take a look at all of the tests that we've done on all of the SMT parts, we've never done a test with power applied to the board. They've all been passive tests to see if we have continuity, if there's a connection. Part of the reason for that is once you apply power to this board, the spacing between the pins and the ground, and on the PT4115, the ground pin is in the middle of all of the pins. So if you're running 12-volt current into it and you reach in to touch the CSN pin, and if you by mistake bridge it with the ground, you can short out the PT4115. The same is true on the back side, where you would have the WS2811 dim pin, basically 2811 through the transistor to the dim pin. That's a 5-volt that if you bridge, you could damage this as well. And over here you have the switch. So my recommendation is to avoid touching any of these pins directly if you can at all avoid it. There are other places that you can pick up readings that I'll walk through here in a few moments. But if you have to reach in and touch the dim pin, the best way to come about it is you come in high and come down on the diode and say on the outside edge of that dim pin. You don't want to end up in the middle touching it, because I can guarantee you if you will hit the middle and short it out. So what you want to do is you want to hug that barrel and come down on the outside. However, the nice thing about it is, like for the switch, you never have to touch, because the way the wiring of the board is for the switch. The switch is attached to the inductor. It is also attached to this leg of the diode. So if I want to know what that switch is reading, I touch here. I don't have to go in here. And there is no danger of cross-connecting with something else to get that reading. You can also use this connection to get a feel for what's going on with the dim pin. There's a set of measurements I haven't talked about yet, and I'm going to do that now. Since the PT4115, as I stated earlier, is a constant current driver, and it is making adjustments to voltage. The way it makes those adjustments is by adjusting the voltage on the switch pin. If you want a full on, you got 5 volts coming in here, and it wants full voltage coming out here, it will drive that pin to ground, which is near 0 voltage. So if I want to know if I'm expecting 5 volts over here, if I check the diode and it's not close to 0, let's say I've checked it and it's reading 12 volts. One of two conditions have occurred. 1, 5 volts are not going in, or 2, the PT4115 is damaged. There's actually a third condition, and that is it will only drive to ground if it's sensing current. And I'll go more into this in a few minutes. But the key thing to understand in trying to pick up that measurement is by reading here, if I get the appropriate reading, I never have to reach in to touch that dim pin. So if I would check here and say I'm not getting what I expected, I would come back to the resistor and say, am I inputting what I expected? And if the answer is yes, then and only then would I ever consider touching the dim pin. And most cases you don't have to. What are some of the other problems because of the fully populated board? Well, if you want to check voltage, why would you ever need to touch the CSN pin, the ground, or the VIN? The answer is there's never a reason to touch them. It doesn't matter. The VIN pin is for voltage coming in to the PT4115. So if you want to know if you got voltage, check the front leg of the diode, because the front leg of the volt here is tied to that pin. If you have continuity, you know it's connected to the board, so if voltage is flowing in, it'll be over here as well. So never have to touch that. CSN pin, do I try and reach in and grab you? Well, why? If I want to touch this CSN pin, all I got to do is touch this part of the, this leg of the resistor. You should know that because that's where we touched to find it from a passive perspective. If I want to touch this one, it's the middle one. You just come right up this line. So again, there's no reason to even to go in to these spots. That way you avoid any chance of shorting it out. Some of the other places or other concerns with the crowded board. There is no good place on this board to pick up a ground. Part of the reason for it is I don't do ground on the board. All of my grounds are attached to the power supply, so I only have to deal with a single probe. So, but if you want to come in and try and get to ground and you reach in and try and touch here, you can do it, but if you make a mistake and bridge, you can short out the board. So as you're probing in these cases, you want to be very careful to make sure you're hitting the proper spot. Should I ever have to hit that positive one? No, that's why I have this one. Same way with the 5 volt. You come over here. And that's the big part of it, is just knowing where to pick it up. You've got your test points out here. There's nice spacing between them. You'll be able to isolate it. If for some reason you run into a problem, you can always turn it over, and if you'll notice, you got really big targets there, but you want to stay out of the space between them. So from a crowded board perspective, there's at least 2 ways to get any reading. Just use the one that makes the most sense and is the safest. Let's move on to the last set of considerations of a fully board. The board is complex. There's a lot of interconnections. For example, to get the signal out to here, you have the WS2811, which is sending signal to the transistor that's inverting that signal, sending it to the PT4115. The 4115 is sending it back through an inductor all the way back out to here. So plus it's got resistors for the current sensing. It's got data inputs, data outputs. So what you have to do is go through a structured process to walk through all of the connections and make sure the measurements meet the expectations. So you need to understand what you expect based on the scenario that you have. For example, I'm expecting a red light, I don't have it. Well, to get that red light, I would expect this to be at 6 to 8 volts. If I'm getting 6 to 8 volts, then I know the problem from this point back is not where it's at. If I got 6 to 8 volts here, then I know the connection is more than likely a problem here. I will go over and verify that I have 12 volts here, which says I'm getting the positive side in, and I'm getting a reading over here when I've got these two across that says 6 volts. Remember, this is the negative side. It's not really going to give you a reading on its own. So when I talk about voltage on this side, it is the pair between the positive and the negative. So when I check from the positive to the negative, I've got 6 volts, therefore I expect that light to be on. If I have a light that's on that I expect to be off, it's the same question. I check from here to here, do I have voltage? If I have voltage, my expectation is I would not have voltage, so I would move back here to find out what's driving this to ground. But let's say it's, again, I've got a light that's on, but I check here, I get no voltage. Oh, okay, that's easy. Again, it goes back to the soldered connection between the LED and the board. It may be a scratch solder mask that's basically grounding this pin. If that pin is grounded, it is going to be on. It'll be on bright. And if it's grounded erroneously, it's going to fry this LED because it will be driven at the full current capabilities. It'll be driven at 12 volts, and it will be the full current that your power supply can generate. So it will pop the LED very quickly. And that's the other point, is if I'm not getting a reading that I expect, I've checked here, I've checked here, I've looked underneath, everything looks good, then what I would actually do is apply a power source across this to make sure the LED even works. So it could be a bad LED. So what you have to do is isolate and work through until you figure out where the component is that fails. Now let's work our way back. I talked earlier about a set of test readings I haven't really talked about. Because of the constant current driver, and it needs to make adjustments for the flow of electrons, the way that is accomplished is by driving switch to ground. So if I'm getting the reading I expect here, I will actually, the next test I'm going to check is the switch. Is it being driven to ground? So again, in this scenario, I expect the light to be on, and it's not. I read here, and basically I'm getting no voltage between these 2 points. So the question is the PT4115 driving to ground? So I would check, in the case of blue, I'd come back here and check this one, and it should be near 0. If it's not, then the question is, okay, dim pin. If this is not being driven to ground, the question is then what's coming on the dim pin. Well, remember I warned you not to touch the dim pin if you can avoid it. So before I would touch that pin, I'd come back here to make sure I'm getting good data signal. Yep, that's been driven to near 0. Therefore, if this is near 0, transistor should be putting out close to 5 amps to here. So in that scenario, I would make the exception and work my way in to test that point. If I'm getting 5 volts here, but this isn't being driven to ground, then I have a problem with my PT4115. 90% of the time, actually 99% of the time, in that scenario is going to be the PT4115. But there is a rare circumstance where it's not being driven to ground because the CSN is not reading current being consumed. So maybe you've skipped the last set of passive tests this thing freed up, it's no longer making a connection. So I would do a passive test from the positive to here to the top of the pin to make sure it was okay, and if it rings with a continuity tester, then it's a bad PT4115. If it doesn't ring, i.e. it doesn't show continuity, then the problem would be for blue, it would be with this resistor. So then I would inspect that resistor. So what it really comes down to is you try and go through a set of tests to get to the point, and then you say, okay, what else could it be, and you try and eliminate those other points. Now, there's a way to confirm whether or not I have a PT4115 that's bad, and that is by checking the continuity between the DIMM pin and the switch. So again, no power on the board. You take your multimeter, set it to continuity, and you check the continuity between the DIMM pins and the switch pins. It should read in excess of 15 mega ohms. Again, 15 mega ohms. In my experience, it's typically higher than that, but it's kind of a barrier that I've found. 15, 16 mega ohms, the PT4115 is generally good. If it's below 15, the PT4115 has experienced some level of damage, and it cannot properly adjust the voltage on the switch pin. And I've seen these drop all the way down to hundreds of ohms, and that's just basically anything coming in is coming out. So I'm pumping 12 in, I'm pumping 12 out. And because I'm pumping 12 in, I'm pumping 12 out, this is nowhere near ground, therefore I don't have a complete circuit between these two. So the way to check it is check it here. If all of this checks out, then you always go back to the resistor. If this doesn't check out, let's say I took the reading and I'm not getting 5 volts, then I would step back and look at the transistor. I've got the right signal coming in, I don't have the right signal coming out, so now I'm going to check for splatter. Is this being driven to ground, whatever the case may be, but now I've isolated the problem to here. There's one other scenario that I want to talk about, which would be I have a light off, but I expect it to be on, and I've taken a reading at the DIMM pin, and it's 0 volts. I come back here and check the data input from the 2811, and it's showing 5 volts. Where did the 5 volts come from? And if I'm getting 5 volts on the data pin, remember the transistor inverts it. What's 5 volts inverted? 0. Therefore, the PT4115 is doing exactly what it's supposed to do. It's supposed to keep, should not be driven to ground. So what can cause that scenario? Well, you've bridged a connection between the DIMM pin and the corresponding 5 volt pin sitting right next to it on the resistor. So if there's a little solder splunk between the two, and it could be very hard to see, that's the exact source of that pin being driven that high. Or should I say it's being driven that low because it's getting a high signal out. So if you read over here and you get a 5 volt, even though you may not be able to see it, you need to clean up the connections between these two. But the big thing is a structured process working from front to back or back to front, taking a reading and checking it against an expected reading. So for every measurement you take, based upon the color that you have chosen, you should have an expectation of what that reading should be. And you probe until you can explain why it does not match that color or that level. So every reading should match, and when you find one that doesn't, you want to make sure that it's not anything that's directly attached to it, and if it is, and if you can make that confirmation, then it is that component, and then you would replace that remove that component, replace that component, and see if it resolved the problem. Sometimes it doesn't. If it doesn't resolve it, then let's say, for example, I just had one the other day that I went through the test, everything looked okay, but when I replaced the PT4115, it still gave me the exact same bad signal. Well, as it turned out, it was a poor solder connection on here. I had a level of continuity, but the connection would not support current at the level that it was being driven. And there was a cracked solder or a cold solder joint that I just flat missed when I was looking at the person's board. So when I replaced this, it didn't change. Therefore, I knew it had to be something with the resistor. So I put the resistor underneath the magnifying glass, found that, yeah, it was a poor solder joint. I actually ended up removing the resistor, put a new resistor in, put power on the board, and everything worked fine. One of the recommendations as we start from the front to the back is, in my experience, the problems more than likely are out here with the LED. When you think about it, we've done a lot of testing on this back end piece, and all we've really checked is this out here. So in the past 2 weeks, I've checked 8 boards. Of those 8 boards, 6 of them were due to poor solder on the LED. The other 2, one was the red PT4115, had been shorted out, and the other board was the blue PT4115 was shorted out. And both of those were verified by the continuity test, and both were replaced, and as soon as they were replaced, everything worked fine. There is one other thing that I will tell you. If someone was to send me a board and they wanted me to look at it, the first thing I'm going to do is remove the LED. That goes back to the section about LED considerations. That way I know exactly how all of the circuitry is going to react. And in my experience, the problem is with the LED connections in here. So the fact I took it off, I'm going to take it off anyway so I can clean it up and make sure I've got a good solder connection. So by taking off, doing my measurements, and then reattaching it, that has generally resolved 90% of the problems. This concludes the video series. My goal in producing this series was to provide you enough information so you would understand the design and be able to troubleshoot problems that may arise as you use and support these flood drivers going forward. I'd like to thank you all for your time, attention, and hopefully everybody enjoys the floodlights this coming Christmas season or whenever you plan to use them. I personally am looking forward to them, and I think they're going to make a dramatic impact to my light show. Again, thank you.